Problems. Rolle's theorem. Problem. Verify Rolle's theorem for f of x, that is x square minus 6x plus 8 in the given domain 2, 4 closed interval. So we have f of x polynomial equation x square minus 6x plus 8. So first condition is f of x should be continuous in the closed interval. F of x should be differentiable in open interval. So check for its differentiation 2x minus 6. So put 2 and 4 value in this polynomial equation to check its equality. 6 of 2 plus 8. So 4 minus 12 plus 8. So 0. F of 4 square minus 6 of 4 plus 8, 16 minus 24 plus 8. So answer is 0. Both are equal. F of 2 is equal to f of 4. So all conditions are satisfied. Rolle's theorem satisfied in the given domain. So by Rolle's theorem there exists at least one real number, say c, in between 2 and 4. So differentiate, in place of x you write down c, that is 2c minus 6 is equal to 0, 2c is equal to 6, c is equal to 3. So 3 is in between 2 and 4. That is, so Rolle's theorem is satisfied. Second problem, f of x, that is x cube minus 4x in a closed interval minus 2, 2. So first condition, f of x is continuous in the closed interval. F of x should be differentiable according to Rolle's theorem. In the open interval, differentiate it 3x square minus 4. So f of x, we have x cube minus 4x. Put f of 2, that is 2 cube minus 4 of 2, that is 0. F of minus 2 whole cube minus 4 of minus 2, that is 0. Both are equal. By Rolle's theorem, all conditions are satisfied. By Rolle's theorem, there exists at least one real c. So f dash of c you get as 3c square minus 4. So 3c square is equal to 4. C square is equal to 4 by 3. C is equal to plus or minus root of 4 by 3. That is plus or minus 2 by root 3. So that is in between minus 2 and plus 2. Third question, f of x is equal to 2x cube plus x square minus 4x minus 2 in the range minus root 2 plus root 2. Proof. First problem, f of x is continuous in the closed interval. F of x should be differentiable in open interval. Differentiate it. 2 3 is 6x square plus 2x minus 4. So f of minus root 2, that is 2 of minus root 2 whole cube plus of minus root 2 whole square minus 4 of minus root 2 minus 2. So 2 cube is 8 minus 4th root 2 plus 2 plus 4th root 2 minus 2, that is 0. F root 2, that is 2 cube. 2 of root 2 whole cube plus root 2 whole square minus 4 root 2 minus 2, you get 0. If you simplify it, both are equal. F of root 2 is equal to f of minus root 2. So all conditions satisfied. All conditions of Rolle's theorem satisfied. By Rolle's theorem, one real c in between the points minus root 2 and root 2 will exist. F dash of c is equal to 0, that is 6c square plus 2c minus 4. In this you put x is c, so 6c square plus 2c minus 4 divided by 2, you get 3c square plus c minus 2. You know it is quadratic equation, you can solve it by method minus b plus or minus root of b square minus 4ac all divided by 2a. You know this formula now. Replace it. So minus 1 plus or minus root of 1 square minus 4 of 3 minus of minus 2 all divided by 2 of 3. So minus 1 plus or minus root of 1 plus 4 3s are 12, 12 2s are 24 all divided by 6. So you get minus 1 plus or minus root of 25 by 6. So minus 1 plus or minus 5 by 6. So you get two values, minus and plus. Minus 1 plus 5 by 6, minus 1 minus 5 by 6. So your answer is 4 by 6, that is 2 by 3. C is equal to minus 6 by 6 minus 1. So fourth problem, f of x, x minus 1, x minus 2, x minus 3 at the domain 2, 3. Proof, given f of x is continuous in a closed interval. F of x, you get x minus 1, you multiply this both, x square minus 3x minus 2x plus 6, that is x minus 1, x square minus 5x plus 6, you get roots. So you get x cube minus 6x square plus 11x minus 6 in the final stage. So f of x is continuous in a closed interval 2, 3. F of x is differentiable in open interval, differentiated x cube, that is 3x square minus x square is 2x, 12x plus 11. Okay. So third condition is this. Put values 2 and 3 in the given polynomial equation. So you get 2 cube minus 6 of 2 square plus level of 2 minus 6, that is 8 minus 4 square. 2 square 4, 6 are 24 plus level 2s are 22 minus 6. So answer is 0. F of 3, 3 cube minus 6 of 3 square plus level of 3 minus 6, that is 27 minus 9, 6 of 54 plus level 3 is 33 minus 6. Answer is 0. F of 2 is equal to F of 3. All conditions of Rolle's theorem satisfied. So by Rolle's theorem we know there exists one real, we can choose any real, not only C, in between the given points 2 and 3. F dash of C is equal to 0, equate to 0, 3c square minus 12c plus level is equal to 0. So C is equal to minus B, apply that formula, plus or minus root of minus 12 whole square minus 4 of 3 of level whole divided by 2 of 3. So 12 plus or minus root of 12 square is 144 minus 4 3s are 12. 12 levels are 132 whole divided by 2 3s are 6. So 12 plus or minus root of 12 whole divided by 6. 12 plus or minus 4 3s is 12. So you can rewrite this as 12 plus or minus 2 root 3 whole divided by 6. 12 by 6 plus or minus 2 root 3 whole divided by 6. 2 plus or minus root 3 by 2. 2 ones are 2 3s are. So 2 plus or minus 1 over root 3. So you can write 3 as root 3 and root 3. Okay. So you get like this, belonging to closed interval 2, 3. Next question, fifth one, verify Rolle's theorem for this polynomial equation f of x, that is log of x square plus ab whole divided by x of a plus b. Given f of x, we have like this. You can expand this logarithm, that is log of x square plus ab. Log a by b is nothing but log a minus log b. And again you can rewrite this as log m into n is there, log m plus log n, minus is there, you can take minus common, log x minus log of a plus b. So first condition, f of x is continuous in a closed interval ab. F of x differentiable, open interval ab. F dash of x you get log x 1 over x, chain rule x square 2x, so log x 1 over x you get minus 0. So answer here interval is a and b. Pick for that f of b is equal to log of b square plus ab whole divided by b of a plus b is equal to log of b square plus ab whole divided by ab plus b square, that is log 1 it is 0. Similarly, you can put for f of a, that is log of a square plus ab whole divided by a of a plus b. So you get log of a square plus ab whole divided by a square plus ab. It is log 1. Log 1 is 0. So f of a is equal to f of b. So all conditions of Rolle's theorem satisfied. So by Rolle's theorem 1, real c will exist, so such that f dash of c is equal to 0. It is 2c by c square plus ab minus 1 over c is equal to 0. 2c by c square plus ab is equal to 1 over c. 2c square cross multiply c square plus ab. So if you shift this to the other side, c square is equal to ab, c is equal to plus or minus root of ab. So this will be the answer. And it also belongs to open interval ab. And root of ab is nothing but gm between a and b. Okay. Last problem. F of x minus a whole power n, x minus b whole power n in open interval ab. Proof: f of x is given polynomial in a closed interval ab. It is continuous. It should be differentiable in open interval ab. When you differentiate it, product rule, n of x minus b whole power n minus 1 plus m times x minus a power m minus 1. So you have 2 points, f of a, f of b. Replace in this, that is a minus a whole power m, x minus b whole power n, that is 0, a minus is 0. Similarly, f of b, that is x minus a whole power m, b minus b whole power n, that is 0. b minus b is 0. So f of a is equal to f of b. All conditions of Rolle's theorem satisfied. So by Rolle's theorem, real c will exist such that f dash of c is equal to 0. c minus a power m minus 1, c minus b power n minus 1, m plus n of c minus mb minus na is equal to 0. That is c minus a whole power m minus 1 is equal to 0, or this term will go to denominator and it will become 0. It is c minus b whole power n minus 1 is equal to 0. c minus a is equal to 0, c is equal to a, c minus b is equal to 0, c is equal to b. And this term will become m plus n of c minus mb minus na. So shift to other side, it will become mb plus na. So rearrange it, mb plus na whole divided by m plus n, where c is nothing but mb plus na whole divided by m plus n belonging to open interval ab. So c divide open interval ab internally. You learnt in your PUC internally, externally. Your addition is this m plus n. So internally in the ratio m is to n. Thank you. In the ratio m is